I'm Nova.
I'm Alloy, and this is AgentStack Daily.
Codex 0.136 added clearer TUI diagnostics, tightened app server lifecycle handling, introduced named hooks with permission scopes, and improved Python and Node SDK behavior around threads, turns, and error propagation. OpenClaw 5.28 remains the current stable harness line with stronger session recovery, sub-agent boundaries, browser validation, and automation guardrails. Hermes 15.2 remains the stable Hermes agent line with multi-agent Kanban, worktree isolation, swarm coordination, and promptware defense, and Claude Code 2.1 latest moved again for teams tracking the CLI package.
The harness news lands first because that is where agent reliability becomes visible. Sessions have to resume cleanly, plugins and hooks have to run under clear permissions, auth and provider routing have to stay governable, browser and terminal surfaces have to fail plainly, and SDK callers need errors that survive the trip back to the application. After the runtime layer, the stack shifts outward. Stanford's agent guidelines turned into a viral engineering reference, OpenAI put frontier models and Codex onto AWS Bedrock, and Expanse showed how cluster-specific telemetry can beat frontier models at predicting GPU resource needs.
The useful thread is concrete infrastructure. Codex 0.136 is about making a local agent runtime easier to inspect and automate. Stanford CS336 guidelines are about turning informal agent behavior into explicit conventions. OpenAI on AWS Bedrock is about putting major model families behind one enterprise control plane. Expanse is about reducing wasted GPU capacity with a model trained on the cluster's own hardware signals.
That is a stack story, but not in an abstract way. A coding agent fails in the real world because the terminal lied, the server kept stale state, the wrong model started, the network dropped, a hook drifted between repos, a permission boundary was too flat, or the team never wrote down what the agent was supposed to do before editing code. These are ordinary failures, and ordinary failures are what separate demos from systems people can use repeatedly.
The model distribution piece matters for the same reason. If OpenAI and Anthropic models are both reachable through AWS Bedrock, a team running agents in AWS can compare providers without redesigning identity, networking, logging, billing, and compliance around every experiment. Model routing becomes more like configuration and less like a special integration project.
Expanse adds the physical economics underneath. If GPU jobs request too much VRAM, memory, and time because no one can predict real usage, expensive accelerators sit allocated but underused. A specialized model trained on DCGM and CUPTI telemetry can know things a frontier chat model cannot know from a prompt: how this cluster behaves, how these users over-request, and where real utilization diverges from declared intent.
So the practical signal is clear: the agent stack is getting less mystical and more operational. Better diagnostics, stronger conventions, cloud-native routing, and specialized telemetry models all move responsibility out of vague model confidence and into surfaces operators can inspect.
Codex 0.136 is the front release because it changes the surfaces that determine whether a local agent run is explainable. The headline is not a new model. It is diagnostics, lifecycle handling, hooks, permissions, SDK behavior, and installation automation. That may sound modest, but those are exactly the areas that hurt when a coding agent becomes part of daily engineering work.
Start with the TUI and Codex Doctor. A failed agent run can look simple from the chat side: the assistant stopped, a tool did not return, or the terminal showed an error. Underneath, the cause can live in several places. The shell environment may be missing a dependency. A provider credential may be present but scoped incorrectly. The repo may be in a state the runtime did not expect. A remote transport may have dropped. The app server may have started with the wrong model. Or the model call may have failed after the runtime had already prepared the next turn.
Better Doctor output gives the operator evidence instead of forcing a reconstruction from scrollback and logs. The release improves readability and adds stronger location and cause information to errors. That matters because something failed is not actionable. The remote transport did not recover before a thread inventory step completed points to a different layer than model selection failed during startup under this provider configuration.
The TUI stability work on macOS and Linux belongs in that same evidence category. Terminal UIs are not passive text dumps. A coding agent TUI streams model output, shows tool calls, displays approvals, renders diffs, tracks status transitions, and updates error panes while multiple asynchronous events are happening. Different terminal emulators, shells, fonts, panes, and control sequences can all expose edge cases.
When the display glitches, operators often blame the agent's reasoning even when the underlying tool execution was fine. A stale spinner can make a completed task look hung. A hidden error pane can make a local configuration failure look like model confusion. A duplicated line can make the transcript feel unreliable. Cleaner rendering does not make the model smarter, but it makes the runtime less haunted.
App server lifecycle handling is the next major change. Codex has a local runtime shape where the app server coordinates important parts of the experience, so startup and shutdown are not just housekeeping. They define the boundary between one run and another, one provider configuration and another, and one remote session state and another.
More reliable model selection at startup is a serious operator improvement. Modern agent setups are increasingly multi-provider. A team may use direct OpenAI access in one environment, Bedrock in another, local models for low-risk inspection, and a different provider for constrained work. If the runtime starts under the wrong model or wrong provider assumptions, the agent can behave differently, cost differently, and violate routing expectations before the user notices.
Cleaner shutdown is just as important. A server that does not stop cleanly can leave port conflicts, stale state, orphaned processes, or misleading continuity. With an agent, stale server state is not only annoying. It can make a new run appear to know things it should not, or make an old run look alive after the operator believed it had ended.
Remote transport recovery is another practical fix. Remote supervision only works if it survives ordinary network reality. People move between Wi-Fi and cellular. Laptops sleep. Home networks hiccup. Remote hosts sit behind corporate gateways or imperfect tunnels. If every interruption forces a full restart, remote agent work becomes fragile. Faster recovery after a temporary network problem lets the runtime preserve the run shape and avoid turning every hiccup into a resume or abandon decision.
Hooks get more structured through named hooks and permission scopes. Hooks are where operators attach behavior to lifecycle events, before a shell command, after a file edit, around a commit boundary, after a plan, after a test run, or when a project policy needs enforcement. Without reuse, teams copy the same hook configuration into every repo.
Copy-pasted hook config is a reliability trap. It begins as convenience and becomes drift. One project has the old hook. Another has the new one. A third has a local edit nobody remembers. If the hook controls logging, notifications, formatting, policy checks, or permissions, that drift is real operational risk.
Named hooks let a behavior be defined once and referenced across configurations. That moves Codex closer to a scriptable agent runtime rather than a one-repo assistant. A team can have a standard pre-command audit hook, a post-edit formatting hook, or a notification hook that becomes a shared building block instead of a hand-maintained snippet.
Permission scopes are the other half. A flat permission set is fine for small use, but real agent work has trust zones. Reading files is not editing files. Running unit tests is not running a migration. Searching local docs is not opening a network connection. Working in a public docs repo is not the same as working in infrastructure code. Scopes let those differences be represented directly.
The Python SDK and Node SDK updates matter for embedding Codex into larger systems. Thread management is about representing task and conversation state cleanly. Turn handling is about the boundary between model output, tool execution, user intervention, and the next model call. Error propagation is about keeping enough information intact that the caller can decide whether to retry, switch models, ask for approval, repair configuration, or stop.
Non-interactive installation is the final practical piece. Codex behaves more reliably when installed with its non-interactive environment flag. That matters for configuration management, container setup, remote workstation images, and CI-adjacent environments where nobody is clicking through prompts. It is not a full deployment strategy by itself, because teams still need credential placement, sandboxing, routing policy, and update control, but it is a necessary primitive for automated rollout.
OpenClaw 5.28 frames the same reliability trend from a different harness. Its stable line-hardened session recovery, timeout and abort cleanup, sub-agent boundaries, browser validation, and automation input handling. Those changes reduce ambiguous state, ghost sessions, stale continuations, malformed tool calls, and helpers bleeding state across workspaces. Different product, same operator demand. Preserve coherent state when the agent is allowed to mutate the world.
Hermes Point 15.2 adds the multi-agent coordination angle. Its Kanban surface, auto-decomposition, swarm coordination, scheduled tasks, worktree per task isolation, model overrides, promptware defense, and secrets manager support are about moving from one agent in one terminal to several managed workers. The core question becomes visible ownership: who is doing what, in which workspace, under which model, with which permissions, and with what evidence.
Claude Code 2.1 latest is smaller in the verified release picture, but the packaging distinction matters. Many teams track the CLI through NPM. The latest channel and the stable channel are not the same operational choice. A group that pins stable is optimizing for controlled rollout. A group that follows latest is accepting faster movement. For a CLI embedded in engineering workflows, that is supply chain posture, not just version trivia.
The reaction across these harness updates is consistent. Operators reward releases that reduce ambiguity. Better diagnostics, named hooks, permission scopes, recoverable transports, isolated work trees, and explicit package channels are not glamorous, but they are the surfaces that decide whether agents can run inside serious workflows without becoming invisible risk.
The caveat is that reliability claims only prove themselves in messy environments. A transport improvement can still behave differently behind a corporate proxy. A Doctor command can still miss a weird shell path. Named hooks can reduce duplication while still requiring governance. The direction is strong because the releases are attacking the right failure surfaces. The value shows up when those surfaces survive real work.
Stanford CS336 course, Language Modeling from Scratch, published a formal AI agent guidelines document, and the developer community treated it as more than a course artifact. It reached 1,863 stars in under 24 hours, which is a striking signal for a file whose purpose is telling students how to work with coding agents.
The interesting part is not that Stanford invented agent guidelines. Many teams already have some form of them: Claude.md, Agents.md, cursor rules, project instructions, repo policy, local conventions, or the prompt people paste at the start of a session. The interesting part is that a formal course made those conventions explicit and the broader community immediately recognized the need.
The document covers task decomposition, tool use conventions, context management, verification expectations, and reasoning about agent output quality. Those are exactly the places where agent work breaks. The model may be able to write the code, but the task may be decomposed poorly, the tool sequence may be wrong, the context may be stale, verification may be shallow, or the model may describe uncertainty as if it were proof.
In an academic setting, those issues affect fairness and reproducibility. If one student uses an agent as autocomplete and another uses it as an unsupervised worker, the learning outcome becomes hard to compare. If students submit generated code they cannot explain, the course has an assessment problem. If agent usage is hidden, instructors cannot tell whether the work reflects understanding, tool operation, or blind acceptance.
Formal guidelines make the boundary visible. They can say what kind of help is acceptable, what must be verified, how generated output should be inspected, and what responsibility stays with the human. That is not anti-agent. It treats agents as real tools that need operating rules.
The same logic applies to software teams. Informal agent habits become invisible process. One engineer may let an agent rewrite a module and accept the difference. Another may restrict the agent to local edits. Another may generate tests but not implementation. Another may let the agent run commands automatically. Without a shared convention, the team's real process fragments.
A Claude.md style or Agents.md style file gives the team a place to encode expectations. It can tell the agent how to explore the repo before editing, what commands are safe, which directories are generated, which tests are meaningful, how to summarize changes, and when to stop for confirmation. It can also tell the human what evidence the agent should produce before the work is considered done.
The key distinction is between guidelines as prompt flavor and guidelines as engineering control. Prompt flavor says, be concise or act like a senior engineer. Engineering control says, before changing the parser, inspect the grammar fixtures, do not edit generated clients, run the narrow parser test before broader checks, if the public API changes, update migration notes, never update a snapshot without explaining the semantic change.
The viral reaction suggests that many developers know their conventions are underspecified. They have enough experience with agents to know that just ask the model is not enough, but not enough shared language to standardize behavior across a team. Stanford's document gives them a concrete reference, even if the priorities came from a course.
There is also an evaluation angle. If two groups say an agent performs well or poorly on coding tasks, but one group provides detailed context and operating rules while the other uses a bare prompt, they are not evaluating the same system. The model is only one component. Instructions, tools, permissions, and environment are part of the agent. Formal guidelines make that composite system easier to compare.
For builders, the best adaptation is to treat the document as a starting point, not as sacred text. Academic guidelines may emphasize learning, explanation, and independent reasoning. A production team may emphasize incident safety, code ownership, review boundaries, generated file rules, deployment limits, and secret handling. A research team may emphasize provenance, experiment logs, and reproducibility. The structure transfers even when the priorities change.
There are limits. A guidelines file cannot force perfect behavior. It cannot replace sandboxing, permissions, review, or tests. It can become stale. It can grow into contradictory advice. It can overfit to one model's habits and become awkward when the team changes runtimes. But those are maintenance problems, not reasons to avoid the pattern.
The best version is concise enough that an agent will actually use it and concrete enough that it changes behavior. A file full of generic values does little. A file that explains the repo's traps, generated paths, meaningful verification commands, review expectations, and uncertainty rules gives the agent a better starting point.
The release lands because agent work is moving from individual experimentation to shared practice. Once multiple people and multiple agents touch the same codebase, conventions stop being optional. They become part of how the team preserves quality while increasing automation.
OpenAI made GPT 4.5, the O-series models, and Codex available through AWS Bedrock, completing a major enterprise distribution pattern. Anthropic's Claude has already been available through Bedrock. Now both major lab families can sit behind the same AWS model access surface.
Bedrock matters because it is not merely another endpoint. For enterprise teams, it connects model access to AWS identity, networking, governance, logging, procurement, quotas, and billing. A team already running workloads in AWS can use familiar primitives, IAM policies, VPC configurations, private connectivity patterns, CloudWatch logs, regional controls, and centralized cost management.
That changes AgentStack design. Without a shared cloud surface, multi-lab routing often means separate credentials, separate SDKs, separate logging paths, separate compliance reviews, separate network exceptions, and separate failure modes. With OpenAI and Anthropic available through Bedrock, model selection becomes more like configuration inside an existing cloud boundary.
For OpenClaw, Hermes, Codex, and Claude code operators, provider diversity no longer has to imply integration sprawl. A team might prefer Claude for long planning or careful review, OpenAI's O-series for reasoning-heavy tasks, GPT 4.5 for broad language work, and Codex for code-oriented flows. Bedrock gives those choices a common operational doorway.
Identity is especially important for agents because tool calls can touch real systems. When an agent reads a repo, queries internal docs, inspects logs, runs commands, or prepares deployment changes, the model call is part of an auditable workflow. Teams want to know which principal invoked the model, from which environment, under which policy, with what timing and cost.
IAM guardrails do not solve every agent safety problem, but they provide a familiar control layer. An organization can scope which roles can invoke which model families, which environments can access which endpoints, and how usage appears in logs and cost allocation. That is easier to govern than developer-owned API keys scattered across laptops, scripts, and local environment files.
DPC-bound access is another major difference. Some teams are not comfortable sending agent traffic through arbitrary public routes, especially when prompts may include code, logs, customer-adjacent data, infrastructure names, or architecture details. A cloud-native route lets them keep traffic inside approved network patterns and connect model access to the existing security posture.
CloudWatch logging also matters after something goes wrong. If an agent run makes a bad recommendation, retries too aggressively, or burns unexpected tokens, the operator needs a trail. Not necessarily a full transcript in every environment, because privacy and retention rules vary, but enough metadata to understand model choice, timing, error rates, retries, throughput, and cost.
For Cloud Code operators, the Bedrock angle connects with Managed Cloud Auto Mode. When the CLI can operate through provider-backed managed environments, model routing becomes part of the same trust conversation as permissions and execution boundaries. Adding OpenAI models to Bedrock means multi-lab routing can happen inside that managed cloud posture rather than through a separate OpenAI integration path.
There is a cloud market signal here too. Major labs choose hyperscaler distribution because enterprise AI buying is not only about benchmark position. It is procurement, compliance, identity, regional availability, auditability, support, and existing spend commitments. A model that is easier to buy and govern can win workloads even when another model looks stronger in a narrow benchmark.
This does not make model choice irrelevant. Latency, throughput, rate limits, context behavior, tool use quality, structured output reliability, and cost can vary significantly across models and routes. A Bedrock-hosted model may not behave identically to direct access in every operational detail. Features, streaming behavior, version availability, regional support, and quota handling can differ.
So the announcement is a capability opening, not a final architecture decision. The useful claim is that the root exists. The unresolved details are how each model performs under real agent workloads, codebase size, tool call frequency, context length, retry behavior, concurrency, output constraints, and approval patterns.
The bigger shift is that enterprise agent stacks can become genuinely multi-lab without becoming bespoke. A team can send summarization to one model, planning to another, code generation to another, and review commentary to another while holding more of the surrounding infrastructure constant. That lowers switching costs and makes experimentation less risky.
The caution is that routing can become complexity theater if it is not evidence-based. If every task has a different model for vague reasons, debugging becomes harder. The mature pattern is to route on observable differences: latency, cost, success rate, tool call correctness, review quality, context retention, and failure behavior. Bedrock makes those comparisons easier because identity, logging, and network posture can stay more consistent.
The dual lab pattern is therefore less about cloud politics and more about operational leverage. The agent runtime no longer has to carry the full burden of provider diversity. The cloud control plane can absorb more identity, logging, and access management work, leaving the harness to focus on sessions, tools, permissions, context, and user experience.
Expanse is interesting because it challenges a common assumption: the most generally capable model is not always the best model for a narrow operational prediction task. Expanse focuses on GPU resource prediction for HPC and cloud clusters, and its claim is that cluster-specific fine-tuned models can outperform frontier LLMs by 8x on that job.
The problem is simple and expensive. GPU jobs often request more resources than they need because the submitter does not know the true runtime profile in advance. They overrequest VRAM to avoid out-of-memory failure. They reserve more time to avoid cancellation. They ask for memory or utilization headroom because underestimating feels worse than wasting capacity.
At cluster scale, those defensive choices become a major efficiency problem. Expanse cites 59% compute waste on national HPC clusters, with one cluster losing roughly $8.5 million per month in wasted compute. Those numbers need confirmation in each environment, but the phenomenon is familiar to accelerator operators. Queues are long, utilization is uneven, and requested resources often diverge from actual usage.
Expanse installs as a lightweight daemon on Slurm and Kubernetes nodes. That is important because those are two major scheduling worlds. Slurm is common in HPC, universities, national labs, research clusters, and large training setups. Kubernetes is common in cloud-native ML infrastructure, inference platforms, and teams that package workloads as containers.
The telemetry comes through DCGM and CupTie. DCGM, NVIDIA's data center GPU manager, exposes hardware-level health and utilization signals, GPU utilization, memory usage, temperature, power, error conditions, and related operational metrics. CupTie, the CUDA profiling tools interface, gives lower-level visibility into CUDA activity. Together, they show what jobs actually do to the hardware rather than relying only on what users request.
That distinction is the product's core. A frontier LLM reading a job description or code snippet can reason broadly about what the job might require. Expanse watches actual cluster behavior. It learns from hardware telemetry, submission history, workload patterns, and local environment details. The model is cluster-specific rather than generic.
Cluster specificity matters because two clusters can behave differently even when they run similar categories of work. Hardware generations differ. Driver versions differ. Container images differ. Users develop local habits. One group runs small inference jobs, another runs distributed training, another runs simulation, rendering, genomics, or quantitative workloads. Scheduler policy and failure history shape what normal means.
A generic model may know that batch size affects VRAM, sequence length changes memory pressure, and mixed precision can change throughput. It does not know that this cluster's users routinely overrequest a particular GPU class, that jobs from one workflow consistently use less memory than declared, or that one queue has a history of underutilized reservations.
Expanse's benchmark claim is that its approach beats GPT 4.5, Claude Opus 4.8, Gemini 3.5 Pro, and Codex 5.3 by 8x on GPU resource prediction accuracy. The striking detail is that model size does not correlate cleanly with accuracy. Claude Haiku reportedly beats Opus on some workloads. That is exactly what you would expect if the task depends more on local telemetry and calibration than on general reasoning depth.
This is an important lesson for AgentStack builders. A general model can be excellent at planning, code synthesis, explanation, and broad reasoning while still being the wrong tool for a domain-specific prediction. If the signal lives in hardware metrics, queue history, job traces, and local patterns, then the model that sees those signals can beat a bigger model that only sees a prompt.
Resource prediction has several concrete outputs. VRAM prediction helps decide whether a job fits on a given GPU without wasting a larger device. Utilization prediction identifies jobs that reserve expensive accelerators but do not use them effectively. Memory prediction reduces crashes and overallocation. Runtime prediction can improve queue placement and scheduling fairness. Together, these can increase effective capacity without buying more hardware.
The line-level optimization angle is notable too. Expanse says it can suggest code-level changes against actual resource usage. That means it is not only saying, request less memory. It may identify patterns creating pressure or waste, inefficient batch size, unnecessary tensor retention, avoidable data movement, poor precision choice, or code that keeps memory alive longer than needed.
That bridges cluster operations and developer workflow. A cluster admin may know that a user's jobs are wasteful but not have a clean way to explain why at the code level. A developer may understand the code but not see hardware telemetry. A tool that connects telemetry to optimization suggestions can make that conversation much more productive.
The caveats are real. Benchmark claims need independent replication. The 8x number depends on task definition, data distribution, baseline prompting, evaluation metrics, and what counts as a correct prediction. A national HPC cluster is not the same as a startup inference fleet. A Kubernetes platform with predictable services may have a different waste profile than a research cluster running one-off experiments.
The non-invasive integration posture still matters. A daemon that observes and predicts is easier to adopt than a scheduler replacement that demands full control immediately. Cluster operators are cautious because the scheduler is critical infrastructure. If a tool begins by measuring, predicting, and recommending before enforcing, it can build trust gradually.
Expanse also points at a broader efficiency future. The next savings wave will not come only from better GPUs, better kernels, quantization, or cheaper inference APIs. It will also come from predicting what resources a job actually needs before it runs. Waste is capacity already purchased but not effectively used.
That becomes even more important as agents generate more experiments, fine-tuning jobs, evaluation runs, batch inference, and GPU-heavy code paths. If agents make it easier to submit work, they can also make it easier to waste hardware. A resource prediction layer becomes part of responsible automation.
The feedback loop will need care. If predictions influence user requests, and those requests shape future scheduling and telemetry, the model must avoid reinforcing bad assumptions. A cluster-specific system needs careful handling around new workloads, new hardware, changing user behavior, and rare high-resource jobs that genuinely need what they request.
Still, the core claim is compelling because it is grounded in a real bottleneck. The AI industry talks constantly about model intelligence, but a lot of money disappears in the plumbing around model work, idle GPUs, over-reserved jobs, queue inefficiency, retry storms, failed runs, and mismatched hardware. A specialized model trained on the right telemetry can create more value than a frontier model used generically.
The project radar has 3 layers: hardware agent operating systems, lightweight terminal context, and scheduling for AI-operated physical machines. These are early projects, but each points at a real gap.
Anima from Full AI is an open-source agent OS for hardware intelligence, targeting IoT devices, robotics, and edge agents. That matters because most agent discussion still assumes a cloud VM or developer workstation. The agent reads files, calls APIs, runs shell commands, edits code, and maybe drives a browser. Hardware agents face a different operating environment.
A hardware agent has to reason about physical state. Sensors are noisy. Actuators can fail. Timing matters. A command can have irreversible physical consequences. The world keeps changing while the model is thinking. Latency, power, thermal limits, connectivity, and safety boundaries matter in ways that are less visible in cloud-only agents.
An operating system layer for hardware agents suggests a more structured approach than bolting an LLM onto embedded Linux and exposing raw tools. The OS can represent devices, sensor streams, hardware permissions, local state, edge constraints, and coordination between perception and action. It can give the agent a controlled interface to the physical world.
Anima is early, with modest visible adoption and very recent activity, so the posture is curiosity rather than assumption. The category is the important stack angle. As agents move into robotics, smart homes, industrial tools, lab automation, and field devices, the runtime cannot just be a chat loop with shell access. It needs hardware-aware abstractions.
CTX from Smarthomio sits at the opposite end of the complexity spectrum. It is a terminal context manager that generates .ctx.md files for coding agents. The pattern is intentionally simple. A markdown file in the repo carries persistent working context across sessions.
Coding agents suffer when every new session begins with amnesia. Transcript-only context is fragile. If relevant decisions happened in a previous run, the agent may not see them. If the human has to re-explain project conventions every time, the agent becomes slower and less consistent. Full memory systems can help, but they add setup, indexing, retrieval, governance, and maintenance overhead.
A.ctx.md file is the lightweight middle path. It can preserve current task state, repo conventions, open questions, known pitfalls, branch context, testing notes, generated file warnings, or design decisions. The agent reads it at the start and has a better map before touching code.
The trade-off is that a context file is not intelligent memory by itself. It does not automatically know what matters. It can go stale. It can grow too long. It can include outdated assumptions. It does not replace semantic search, code graphs, local MCP servers, or knowledge graph memory. But its simplicity is the point. A file in the repo is transparent, reviewable, editable, and portable across agents.
For teams, this becomes a social object. A human can edit it. An agent can propose updates. A reviewer can see whether context changed. If the file says, "Do not edit generated API clients," and an agent edits one anyway, the failure is easier to diagnose. If it says, "The migration is blocked on schema review," a new session can avoid charging ahead as if the path were clear.
Agent Grid from Hanfihu is an open scheduling layer for AI-operated physical machines, tools, and desktops. It sits below the agent runtime and decides when and how physical actions get dispatched. That is distinct from deciding what the agent wants to accomplish.
Digital tool calls are often treated as instantaneous or reversible enough to retry. Physical actions are not like that. A robot arm cannot occupy two positions at once. A lab instrument may need warm-up time. A desktop automation task may require exclusive screen control. A machine tool may have safety interlocks. A smart home action may depend on time, occupancy, or sensor state.
A scheduling layer makes those constraints explicit. Instead of the LLM directly sequencing every action, the agent can request actions and the scheduler can coordinate timing, exclusivity, dependencies, and physical constraints. The model can reason about goals and plans, while the scheduler enforces execution reality.
This becomes more important when multiple agents or users share physical resources. If two agents want the same machine, the system needs arbitration. If one action must complete before another begins, it needs dependency tracking. If a physical action has a safe time window, it needs timing awareness. Prompt text is a weak place to encode all of that.
The project is very early, with tiny visible adoption, so it is a radar signal rather than a mature platform. But early projects often reveal where the pain is heading. As AI agents leave the browser and terminal and begin touching devices, scheduling becomes a core layer.
These projects also connect to context management. Anima needs hardware context, sensors, device state, physical constraints. CTX needs repo context, task state, conventions, and open questions. Agent Grid needs action context, availability, timing, exclusivity, and dispatch state. Different agent layers need different memory and scheduling primitives.
The .ctx.md pattern deserves the extra attention because it sits between two common extremes. Transcript-only context is easy but brittle. Once the session ends, the memory is gone or buried. Full semantic memory can answer richer questions and scale across larger code bases, but it requires infrastructure and can introduce stale indexes or retrieval errors.
Lightweight context files preserve the few facts that matter without turning context into a hidden system. They work well for active branches, migrations, small teams, repo-specific rules, and projects where humans want visibility into what the agent believes. They are less powerful than knowledge graphs, but easier to inspect and correct.
The subtle failure mode is stale authority. If a memory layer says something confidently and the repo has changed, the agent may follow old guidance. A visible context file can reduce that risk because humans can read it directly, but it can still become stale. Knowledge graphs can automate more retrieval, but they can hide mistakes behind a polished answer. Transcript-only context avoids persistent staleness but loses continuity.
The principle is freshness and authority, not just more information. A current convention should be treated differently from a hypothesis. A completed task should be treated differently from an open question. A generated note should be treated differently from a human-approved policy. CTX is interesting because it makes that working context visible.
Hardware agent systems need the same discipline. Anima-like OS layers and agent grid-like schedulers can expose physical context in structured ways, device state, sensor readings, constraints, action cues, and safety boundaries. Without that, the model has to infer the physical world through brittle tool descriptions and delayed feedback.
The radar items show the agent stack widening. It is no longer just model, prompt, and tool. It is runtime, context file, memory layer, hardware OS, scheduler, cloud model surface, telemetry model, and permission boundary. Each layer exists because raw model capability does not solve operational coordination by itself.
Codex 0.136 is the immediate runtime release to understand. Its value is readable doctor output, better error location and cause, more stable TUI rendering, cleaner app server startup and shutdown, more reliable model selection, faster transport recovery, named hooks, permission scopes, SDK improvements, and more dependable non-interactive installation. Together, those make local and remote agent operation less ambiguous.
OpenClaw 5.28 and Hermes 15.2 frame the same trend around state and coordination. OpenClaw emphasizes recovery, session boundaries, sub-agent isolation, browser safety, and stricter automation inputs. Hermes emphasizes multi-agent work surfaces, Kanban, decomposition, swarm topology, worktree isolation, scheduled tasks, model overrides, promptware defense, and secrets handling. The common theme is managed workers rather than loose conversations.
Cloud Code 2.1 latest belongs in the operational picture because package channels matter. A CLI used inside engineering workflows is part of the runtime supply chain. Pinning stable and tracking latest are different risk decisions, especially when the tool runs on developer machines, managed workspaces, or CI-adjacent environments.
Stanford's CS336 guidelines are the clearest sign that agent behavior conventions are becoming formal infrastructure. A guidelines file gives humans and agents a shared contract: how to decompose tasks, what tools to use, how to manage context, what evidence is expected, and how uncertainty should be handled. The viral reaction shows that developers were waiting for a concrete reference.
OpenAI on AWS Bedrock changes model distribution for enterprise agents. With GPT 4.5 O-series models and Codex available beside Claude, teams can route across major labs from one cloud control plane. IAM, VPC patterns, logging, quotas, billing, and compliance reviews can cover more of the model surface. Multi-lab routing becomes less of a custom integration project.
The caveat is that Bedrock availability is not identical behavior across every route. Teams still need to understand latency, throughput, cost, feature parity, regional support, streaming behavior, quota limits, and how each model performs under tool-heavy workloads. The value is that those comparisons can happen inside a more consistent operational environment.
Expanse is the reminder that specialized infrastructure models can beat general frontier models when the signal is local and measurable. GPU resource prediction depends on cluster telemetry, user behavior, scheduler patterns, hardware generation, and workload history. A cluster-specific model that sees those signals can outperform a larger general model that only reasons from text.
The economic implication is direct. Reducing wasted GPU allocation can unlock capacity without buying new hardware. That matters for research clusters, training platforms, inference fleets, and any organization where accelerator access is a bottleneck. As agents make it easier to generate and submit compute-heavy work, resource prediction becomes even more important.
The project radar fills in the edges. Anima points toward hardware-aware agent operating systems for IoT, robotics, and edge devices. CTX points toward lightweight persistent context through .ctx.md files. Agent grid points towards scheduling layers for physical machine actions. These are not interchangeable tools, they are signs that the stack is spreading into physical state, working memory, and coordinated action dispatch.
The context management takeaway is simple. Not every team needs a full memory system. Transcript-only context is often too weak, full knowledge graphs can be too heavy, and a visible context file can be the right intermediate layer. The best memory layer preserves the facts the agent needs without turning stale notes into hidden authority.
The operational takeaway is that infrastructure is becoming visible. Diagnostics make failures explainable. Guidelines make expectations legible. Bedrock makes model routing governable. Telemetry models make compute waste measurable. Hardware OS and scheduling projects make physical action constraints explicit. Context files make agent assumptions easier to inspect.
That is what a maturing agent stack looks like. Less mystery, more boundaries, more evidence, and more specialized layers doing the jobs that raw model intelligence does not do well by itself.
Thanks for listening to AgentStack Daily. For links and source details, look at the show notes at tobeyonfitnesstech.com. We'll be back soon.